Hey guys, I'm Alan Mendes and I'll be demonstrating Challenge 1 project for ECE 561 on MSP 432 development board. So for the Challenge 1 project, we have to develop a system on the MSP 432 board that erases, programs and verifies 128 KBs of flash main memory every 1 minute, along with the Watchdog timer trying to reset the system every 1 second, for which the system responds by clearing the Watchdog timer counter or by resetting the Watchdog. So a brief overview of the code or the logic developed for this system is there would be a red LED which would toggle at the beginning of the program, indicating the start of the program or resetting of the system. Once the red LED toggles, the flash programming starts. This flash programming includes erasing, programming and verifying 128 KBs of flash main memory. Once that procedure is done, the green LED toggles for 1 second, indicating the flash programming is complete. After that duration until 1 minute, the system remains idle. At the end of 1 minute, the blue LED toggles to indicate that 1 minute is up. We even have the S2 push button as a user input. The user can press and hold the S2 button to force the Watchdog timer to timeout, thereby resetting the system on the user's input. So now I'll be explaining the code developed for Challenge 1 project in Code Composer Studio. We start off by including the required libraries as seen over here. Then we define an array named sectors containing 32 elements containing the names of all the sectors from 0 to 31. As we have to erase, program and verify 128 KBs of flash main memory, with each sector being 4 KBs, we require 32 such sectors. Hence, the sector names start from flash sector 0 to flash sector 31. Then we initiate an array named as buff_add with 32 elements containing the starting addresses of each sector. Then we define a function named portInit. This function is used to initialize all the required inputs and outputs for the code. In the first line, we see that P10 is made an output, that is the red LED. P14 is made as an input, that is the S2 button, which we'll be using as a user input to force the Watchdog timer to time out and reset the system. In these two lines, we'll be connecting the pull-up register to the input button to avoid switch rebouncing. Here we make P21 and P22 as outputs. These are the green and blue LEDs. The usage of these LEDs will be explained later. Here we switch off the red, green and blue LEDs. We set the wait state of bank 0 and 1 to 2 for flash read operations. Using this function, the delay 1 second, we can generate a 1 second delay. Using this function, the delay 200 milliseconds, we can generate a 0.2 seconds delay. This master clock or the system clock is configured at 1.5 megahertz, that is the default rate. The erase and program flash function will be explained further. Here starts the main program of the code. We initialize two counters, count to define the flash sector number counter, which would define the sector number which will be programming, erasing and verifying. The Watchdog counter is used as a counter to increment a 0.2-second delay between each time the watchdog is restarted. Here we call the port init functions and thereby initialize all the variables required for the code. We start off by halting the watchdog timer while we set up the required parameters. We toggle the red LED to indicate start of program, which is also used as a reset indicator. We turn on the red LED, call the function delay 1 second and then turn off the red LED. Now we start the watchdog timer with a timeout set to 1 second. That means if the watchdog timer counter is not resetted within 1 second, the watchdog timer will reset the system and the code will start from this line. Now we enter the while loop. We initialize count as 0 as we want to start erasing and programming from sector 0. This condition comes from the case where we have 0 to 31 sectors, hence count will be increasing from 0 to 31. Here we restart the watchdog counter within 1 second so that it doesn't reset the system. We now call the erase and program flash function with the parameter count being 0 at this moment. This takes us to the erase and program flash function with the sector number defined to be 0. We initialize a buffer of 4 KBs. We write a pattern of 0x00 into this buffer. We start off by unprotecting the sectors array with the sector number to be 0 points to the first element of the array, the flash sector 0. Hence, this program will be called each time to erase, program and verify each sector. So in this line, we unprotect the sector 0. In the next line, we erase the sector by mentioning the starting address of that particular sector. Right, currently the sector number is set to 0. Hence this array will be pointing to the starting address of the flash sector 0. Now we need to verify if the erase process is done correctly. Hence we call this API verify memory with the starting address, the size and flash 1 pattern. Once a sector is erased, the sector is written with all ones, that is FFFF. Hence we use the flash 1 pattern to compare and verify the erased data. Then we move ahead to program the sector with a new data. The new data is stored in buffer, which is the 0x00 pattern. We mention the starting address over here, the sector number being 0 and the buff add array pointing to the starting address of flash sector 0. And we mention the length of the buffer. At this point, we have programmed flash sector 0 with the pattern mentioned over here. Now we need to verify that the program data in the sector 0 is correct. Hence we use the verify memory with the buff address pointing at the starting address, and we use a flash 0 pattern, as we have written the pattern 00 all throughout the sector. We would verify it with a flash 0 pattern. After the programming is complete, we protect the sector. This array will be pointing at flash sector 0. Once this process is complete, the sector number would be incremented and hence it would be pointing to the next sector, and this process repeats from 0 to 31. All these APIs are mentioned in the while loop that keeps the system idle if there's some error generated while the operation of this API or all the APIs. If the system is kept idle beyond 1 second, the watchdog timer will expire or timeout and hence reset the system. If the system is not resetted, that means all the functions in erase and program flash and throughout the entire code have been completed successfully. Once this program ends, we reach to this point, the count plus plus. This increases the count value and thereby starts pointing at the next sector in the flash sectors array. We use this line to take the S2 button as a user input. If the user presses the S2 button, which when he would like to expire the watchdog timer so that the watchdog timer resets the system, the user can press this button. Again, this while loop will be activated when the user presses the button and would keep the system idle beyond 1 second, which would thereby expire the watchdog timer, which would thereby reset the system. We again reset the watchdog timer with a 1 second expiration. At this point, we have completed the erasing, programming and verifying of 128 KB of flash memory. Hence, to inform the user, we toggle the green LED. We set the watchdog counter as 0. Then we turn on the green LED. We increment the watchdog counter from 0 to 4, and in this while loop we will be resetting the watchdog timer each time as it increments with a delay of 0.2 seconds. And in this line we turn off the green LED. So this code toggles the green LED on and off with a duration of 1 second. In this part of the code, once we are done with the flash programming and toggling the green LED, the time left from this point till the end of 1 minute is the duration when we keep the system idle. Hence we initiate watchdog counter back to 0. And then with the help of delay 200 milliseconds and by resetting the watchdog repeatedly, we can keep the system idle till t is equal to 60 seconds. This while loop is checked every time watchdog counter is incremented to see if the user has pressed the button during each iteration. If the user has pressed the S2 button when the system is idle, it would expire the watchdog and the watchdog would reset the system. This is a piece of code which I have added for more simplicity. As soon as 1 minute ends, the blue LED will toggle to indicate that 1 minute is up. Once the blue LED toggles, we reach this point again where it would start the process of erasing, programming and verifying all the sectors again. Hence, we use the same logic as the green LED for the blue LED and then toggle the blue LED for 1 second. Hence, in short, the program flow goes like: the variables are initiated, the watchdog is halted when we set up the other variables, we toggle the red LED once, we start the watchdog counter, we erase, program and verify all the sectors of the flash memory, resulting into 128 KB. We again reset the watchdog timer. After the process of erasing, programming and verifying is done, we toggle the green LED for 1 second. From that instant till t is equal to 60 or till the end of 1 minute, we keep the system idle while checking if the user has pressed the S2 button for a force reset. Once 1 minute is up, we toggle the blue LED for 1 second. So this completes the code explanation for Challenge 1 project. So now I'll be showing you the output of Flash programming using the memory browser window. Currently, we are at the starting location, that is 0x00020000. As seen over here, all the locations are currently FFFF. We insert two breakpoints in the code just to verify the erase sector and program memory APIs. So we set a breakpoint after the erase procedure is complete and one breakpoint after the programming procedure is done. So I have rebuilt my code and currently in the debug mode. So when I hit play, the program comes and halts at this breakpoint. Currently, as we can see, the data written at this location is FFFF. Now when I hit resume, it gets programmed to the pattern I have mentioned over here, that's 000. This iteration is only for one sector, hence we can see the pattern being written only till the end of first sector, that is till this point. Now when I remove the breakpoints and then resume the code, it should program all the sectors starting from this starting address. So as we can see, all the memory locations are programmed with the pattern 0000 up till the end of 128 KB starting from this location. So this is the end of 128 KBs and the pattern is programmed till this point. Now I'll be showing you the optimization part of the Challenge 1 project. Once I rebuild the project, I get this options in the advice menu. Currently is showing me detecting compilation without optimization. Hence, it recommends me to optimize the code to level 3. Currently, the memory used by the main program is seen over here. So when I click on this advice, it will take me to the optimization menu. Here I can change the level of optimization. I select the level of optimization as 3. Hit OK. And rebuild the project. So now the project will be built by level 3 optimization. So as you can see, the main memory has reduced to 8022 from 10,035. Hence we use different levels of optimizations to optimize the code. So now I'll be showing you the demonstration of Challenge 1 project on the MSP 432 board. Here is my project folder which I would rebuild. So now the project is ready to debug and to burn on the MSP 432 board. So now a red LED should toggle to indicate the start of the code. Once the flash programming is done, the green LED should toggle to indicate completion of flash programming, and after 1 minute the blue LED should toggle to indicate the completion of 1 minute. So here I start my code when I hit play. So as we saw, the green LED toggled, that indicated that flash programming is complete. In this duration, the system will remain idle. At 60 seconds, the blue LED should toggle, and hence it would indicate the end of 1 minute and flash programming would start all over again. We even have a push button user input to force the Watchdog timer to timeout. Hence, when we press and hold it, we can see the red LED toggling, which indicates the system is resetted. And once we leave the button, the flash programming starts and the system repeats itself. Thank you.